So today we're going to talk the seasons, kind of the most basic weather thing you can talk about. Why is it warm in the summer? Why is it cold in the winter? And at some level, the answer actually is pretty simple. It's warm in the summer because we get more energy from the sun in the summer. And it's cold in the winter because we get less from the sun in the winter. But of course, the details are never quite so simple. So we're going to spend some time going through exactly how that works. Now, to get into this, I'm going to start with a definition. I'm going to start with the definition of a term referred to as insolation. Insolation. This is insolation with an O. That's not to be confused with insulation with a U. Insulation is what you put in your house to help keep it cool in the summer and warm in the winter. Insolation is a little bit different. Insolation has to do with the amount of energy coming in from the sun. So to be concrete, let's suppose we think about a little patch of ground on the Earth's surface. And we'll just say, some size, but we'll just say that it's 1 meter squared. So it's a little square out in the middle of a field, a meter on a side, say. So by definition then, the insolation is the amount of energy received from the sun by that little patch of the Earth's surface over the course of a day. So the sun comes up in the morning, and that little patch of the surface starts to receive energy from the sun, and then the amount of energy received goes up until about noon, then it goes back down, and then that's it. So the question is, how much energy did it receive in total over the course of the day? And of course, on average, places that have higher insolation, that are receiving more energy from the sun, are going to end up having higher temperatures. It's not quite that simple, as we'll see. There's a bit of a lag involved, but that's the basic story. When you have higher insolation, the temperatures are going to be higher. Now, if you think about it, you'll realize that this insolation, the amount of energy, is going to depend on two different things. First, it's going to depend on the number of daylight hours. Number of daylight hours, how long your day is. And then second, it's going to depend on the orientation of the surface relative to the sun. So the surface's orientation relative to the incoming sunlight. Now, the first of these two guys is pretty intuitive. If you have a longer day, obviously you're going to spend more time out in the sun, so you're going to get more energy from the sun. The second one's maybe a little bit more subtle, so let's flesh that one out just a little bit more. So let's consider a little thought experiment. Suppose that you're sort of at one end of a darkened hallway, and you're holding a little solar panel. And that little solar panel has a meter on it that says how much energy that it receives, how much energy it's receiving at any given time. And then at the other end of the hallway, one of your friends has a flashlight, and he turns it on and shines it at you and that solar panel. It's kind of one of those police flashlights, has a very direct beam, so he's shining it right at you and the solar panel. And the question is, how much energy does that solar panel receive? What does the meter on it say? And the answer, of course, is going to depend on how you hold it, how you hold the panel. So for instance, if you hold it straight up and down so that it's perpendicular to the incoming light, then you're going to capture a certain amount of energy. As I've drawn it in here, I've sort of got 6 arrows worth of energy coming in, and holding the solar panel straight up and down, it's intercepting 4 of them. So we'll say that it's receiving 4 units of energy. So the meter on your solar panel says 4. Now, if instead you take that panel and you rotate it a little bit, say we rotate it 45 degrees here, now the solar panel is not going to intercept, it's not going to capture as many rays, right? We're still kind of 6 sort of arrows of energy coming in, but we're only intercepting something less than 3. And in particular, if you run the numbers, it turns out to be 2.8. So your meter's going to say 2.8 at that point. Just by tilting the solar panel, you're getting less energy incident on it. And if you rotate it all the way down, so you rotate it a full 90 degrees, so now that it's oriented parallel to the incoming light source, and you hold it just right, now all of a sudden you're not getting any of the energy. So the energy that's coming in is going right by that solar panel, and so in principle it's going to read 0 at that point. So we're not getting any. So clearly the amount of energy we receive then is going to be related to how the surface is oriented relative to the light source, where we get the maximum energy if we're oriented perpendicular to the light source, and then we get the minimum if we're oriented parallel. Now in between, it's pretty straightforward to show that the energy that you get is actually going to vary with the cosine of the angle that you rotate it by. See how that works? We'll just sketch it out. It's a little bit of trigonometry here. And you don't really need to get the details of this down. I just kind of want to show how it works, how you would figure this out. So let's suppose this dotted line is the vertical. So this is the direction perpendicular to the light source. The light source is coming in from the right. And we've got our little panel here. And it's rotated by some angle theta. So this guy here is the Greek letter theta, and it's rotated by an angle theta relative to your straight up and down position. So now we're going to take this and make a little triangle out of it here, like so. And if you think about it, the part of this that matters is this leg of the triangle here, the vertical leg, because that's the leg that's going to determine how many rays of radiation it intercepts. Here. The longer this leg is, the more that you're intercepting, the more energy you're going to receive. So now we just have to figure out how long this leg of the triangle is. So to do that, we just have to remember some basic trig. So first, let's note that the angle that we rotated this guy by theta is also the same as this angle down here, right? Because this is the vertical direction. This is the object, this is our panel, and so this is the same angle here that we rotate it by relative to the vertical. Second, let's say that the size of this panel is A. In principle, this is actually the area of the panel, but as we've drawn it, since it's only two-dimensional, we can just say it's the length of the panel. So A is the size of the panel. And so the question is, how long is this leg here? Well, if you remember your trig, the opposite side is A sine theta. The side opposite to your angle here is going to be the hypotenuse A times the sine of theta. And then the adjacent side to your angle is going to be the hypotenuse A times cosine of theta. So what we find then is that the part, sort of this leg here, which determines how much of the energy that we're intercepting, goes as the cosine of the angle that you rotate it by relative to the vertical. So for instance, in this top figure up here, it's rotated by an angle of 0, right? It's not rotated at all. It's perpendicular. And so in that case, it's going to look like cosine of 0. And cosine of 0 is 1, which is the maximum value cosine can have. So at this point, we're actually receiving the maximum amount of energy. If you rotate it by 45 degrees, now it's going to go like cosine of the 45 degree angle that we rotated it. And cosine of 45 is square root of 2 over 2, which is about 0.71. So by rotating it to 45 degrees, we're now getting about 70% of what we had before. And of course, if we rotate it all the way down, now we've rotated it a full 90 degrees relative to the up and down position. And cosine of 90 degrees is 0, so we're not getting anything. Okay, so that's how it works. Depends on the orientation, and it actually depends on the cosine of the angle made with the perpendicular direction. Now let's put this on the Earth. So to keep things simple, let's say that the Earth is a sphere. It's pretty close to a sphere. It's not exactly, but let's say it's a sphere. And let's just say for the moment, it's got an axis of rotation here. And let's just say that that axis of rotation is oriented perpendicular to the incoming light from the sun. So the light's coming in from the sun over here on the right, and we'll say the axis is perpendicular to that. Now, I'm sure most of you know that that's not right. It's not true. It's not perpendicular. But we're just going to think about this case first, and then we'll see what happens when it's not perpendicular. Now let's go in and consider a little bit of surface. So just like we considered a little patch of ground before, let's consider a little patch of ground on the Earth's surface at different latitudes here. So we've got one at the equator, we've got one at 45-degree latitude, and then we've got one at the poles here. So what do we see? Well, the first thing we see is that at the equator, our little surface is oriented perpendicular to the incoming light from the sun. It's oriented perpendicular to the light that's coming in, and so because of that, it's getting the maximum amount of insolation. So this guy at the equator gets the most insolation you can get. But as we go north or southward and the latitude changes, the surface is going to end up rotating. So as latitude increases, or decreases actually, the surface is going to rotate away from that perpendicular position, and you're going to get less energy, less insolation. And of course, by the time you get up to the poles, now you're oriented parallel to the incoming light, and so you're not getting any energy there. So the conclusion is that in this simple experiment, this simple case where we're oriented with the axis perpendicular to the incoming light, the equator is going to end up having maximum absorption because it's oriented perpendicular, and the poles are going to end up having minimum. And in between, you're going to have it vary from one to the other, and it's actually going to end up varying with the cosine of the latitude in the same way that we just showed that it varied with the cosine of the angle. Okay, but of course, the Earth is not oriented with its axis straight up and down. The axis of the planet, the rotation axis of the planet, is actually tilted with respect to the incoming light from the sun. It's tilted by about 23 degrees, and actually when I made this figure, I tilted it by the same amount. So this figure is actually tilted by the same amount that the Earth is tilted relative to the incoming light from the sun. So now what do we see? And we're thinking about this relative to the case where it was straight up and down. Well, the first thing that we see is if we focus on this guy here at 45 degrees, initially it's rotated at 45 degrees, but if I step it forward, it actually slides down to become a little bit more perpendicular here. So let's do that again. So initially it's up here, it's rotated 45 degrees. Now I step it forward, and it rotated down and became a little bit more perpendicular. So the first conclusion, or the first inference, is that surfaces in the northern hemisphere are going to rotate towards the perpendicular a bit more, which increases the amount of insolation. I should have made it clear, I guess I didn't make it clear before, that the hemisphere here that's being tilted towards the light source is the northern hemisphere. So surfaces in the northern hemisphere are going to rotate a little bit towards more perpendicular. So that increases insolation. Now, if you remember back, insolation had two things it depended on. It was the orientation of the surface and also the length of the day. So what about the length of the day? Well, if we want to figure that out from this figure, we just have to pretend that we're on one of these circles, that we're on one of these latitude circles going around in a circle over the course of the day. And we have to ask ourselves, how much of the day would we spend in the light and how much of the day would we spend in the dark? If we go back to the case where we're straight up and down, In this case, we end up spending exactly half in the light and exactly half in the dark. So we have a 12-hour day and a 12-hour night. But by tilting the planet, we see that now we've put more of this latitude circle here in the northern hemisphere in the light. Right? It's going to spend most of its day in the light, and then there's just a little bit back here in the dark. So in addition to rotating the surfaces to become more perpendicular to the light source, we've also increased the day length. So latitude circles in the northern hemisphere have more daylight hours than before, which also increases insolation. So for both of those reasons, we're getting more energy from the sun now in the northern hemisphere than we were before. What about the southern hemisphere? Well, the southern hemisphere has been tilted away from the light source. And what happens to it? Well, in this case, the surfaces that were at 45 degrees now actually rotate to become a little bit more parallel. Maybe we can step back and show that real quick. So if we think about this guy here initially at 45 degrees here, what happens to it? It actually ends up a little bit more parallel than it was before. So it's exactly the opposite of what happened in the northern hemisphere. We're actually going to be rotating away from perpendicular, and we're going to get less energy. What about the length of the day? Well, for this latitude circle here, it's going to spend only this little bit here in the light, and the rest of it's going to be in the dark. So the day length got a lot shorter. So for both of those reasons, the amount of energy we get from the sun decreases in the southern hemisphere. So for both these points, the opposite happens in the southern hemisphere. So the conclusion that we get is that by tilting the planet relative to the incoming light source and tilting it so that the northern hemisphere is pointed towards the light source, we end up increasing insolation in the northern hemisphere and we end up decreasing insolation in the southern hemisphere. Now, of course, we could tilt the planet the other way, right? We could tilt it so that the northern hemisphere points away from the light source and that the southern hemisphere points towards the light source. And what happens then? Well, in that case, everything's going to be exactly the opposite. These surfaces that were at 45 degrees here in the northern hemisphere are going to rotate a little bit closer towards parallel, so away from the perpendicular. And the latitude circles that were 12 and 12 are now going to end up being less time in the light and more time in the dark. And so as a result, we have shorter days and less perpendicular surfaces in the northern hemisphere, which means we're going to get less energy now in the northern hemisphere. And again, the opposite happens in the southern hemisphere. Down here, the surfaces rotate a little bit more towards perpendicular, and you're going to have longer days and shorter nights. So we're going to end up with longer days and more perpendicular surfaces in the southern hemisphere. The end result then is going to be that by tilting the northern hemisphere away from the light source, which is equivalent to tilting the southern hemisphere towards the light source, we're going to end up having more insolation in the southern hemisphere and less insolation in the northern hemisphere. So if we put these two guys together, the moral of the story is going to be this. So the moral of the story of this little argument is going to be, for a planet that's tilted, our energy received, i.e. our insolation, is going to increase in the hemisphere that's tilted towards the light source. So insolation increases in the hemisphere tilted towards the light source, i.e. towards the sun, so insolation increases in the hemisphere tilted towards the sun. In this case, it's going to be the northern hemisphere. And it's going to end up decreasing in the hemisphere tilted away from the sun. So when the planet is tilted, the hemisphere tilted towards the sun is going to get more energy, and the hemisphere tilted away from the sun is going to get less energy. And this is going to end up explaining the seasons. Basically I said before that in the summer it's warmer because we get more energy from the sun. Well, this is actually going to be the reason why. It's going to be because of the tilt of the planet, and such that in the summer we're going to end up being tilted towards the light source, and we're going to get more energy. Okay, so we'll take a quick break here, and then we'll come back and finish that off with the next screencast.